Okay, everybody, let's pick off where we left off. When we were last together, we had proposition 925. So this ties together some of these notions of ideals, subrings, and so forth. If you have a homomorphism of rings, so remember that preserves the abelian group structure, preserves multiplication, then the image of F is a subring of T, the kernel of F is an ideal. Let me prove this real quick for you. And this will show you kind of the advantage of, what we know already. Number one, so we already know that the image of F is a subgroup of T. Because we've done all this back in the day with groups. This is a ring homomorphism, so first and foremost, it's an abelian group homomorphism, so we already know this is subring. What else do we need for this to actually be a subring? We need this to be closed under multiplication. So let's see what happens there. Let X and Y be an image of F. What does this mean? There exists A, B, and R such that F of A is X and F of B is Y. Right? So let's look at the product. This is F of A, F of B. But again, F is a homomorphism. So this is F of AB. And so XY is in the image of F because AB of F evaluated AB is XY. So image of F is a subring of T. Okay, what about this other business about the kernel being an ideal? Well, to that end, we'll also get a little advantage here too. We know that ker F, let me remind you what this is. This is the set of X in R such that F of X goes to the zero element of T. And of course, the zero element of T is the identity of the group structure on T. This is a subgroup. In fact, back in the group theory days, we know that the kernel of any homomorphism, and remember, F is, since it's a homomorphism rings, it's a homomorphism of groups as well. We know that the kernel is always a subgroup, in fact, a normal subgroup. We don't really need to worry about normal here because the additive part of the ring is abelian, so every subgroup is normal. Now, how about the ideal? I am going to go through the details. I want to prove that this is both a left and a right ideal, and hence an ideal. Let R be an R, and X be in the kernel of F. So in other words, what this means is F of X is 0. So, consider F of Rx. This is F of R, F of X, because this is a homomorphism, and this piece is 0, so the whole thing is 0. And also, this is very similar, except now the F of X is on the other side, but it doesn't matter because it's 0. Again, this is 0. So, Rx and XR are still in the kernel of F. So the kernel of F is an ideal. Oh. Okay. Let me give you the next lemma. And this is rather a silly lemma. But despite the silliness of it, it will be useful much later. And it's a simple observation, and it's a key way to kind of distinguish if an ideal is proper. So before I get into this, let me recall for you that zero and R are always ideals of R. In a very simple, very silly way, they're both subgroups and they're both vacuum cleaners, right? Because you've got either zero and anything times zero is zero, or you've got the whole ring and anything times that is sucked into the whole ring. No problemo there. We say the left ideal. So when I put that in parentheses, I mean, I could be talking about a left ideal or a right ideal if I do the multiplication on the other side, or an ideal where a two-sided ideal or just an ideal where it doesn't matter what side you multiply on, is proper. So what do I mean by proper ideal? If it's strictly contained in I, or strictly contained in R. So it's a proper subset, it's not the whole ring. In a lot of ring theory, you want to pay more attention to proper ideals. They're a more central object of study. As an ideal itself, the whole ring is doesn't give you much information. So here is a result that is fairly easy to prove, but it is it's kind of central here. What do I call this? Lemma, I guess. 926. I'm gonna couch this lemma in terms of ideals. It doesn't matter. You can there's an analogous result for left ideal or right ideal. Well, let's say let I be an ideal. Then I is the whole ring, so I is an improper ideal, if you will. If and only if and I did forget to say that here, so I'm going to say it now. R is a ring with identity. Of course, it doesn't make any sense for me to do this theorem if it doesn't. So if you have an ideal, or I'm sorry, if you have a ring with identity, it can be commutative or not commutative, then an ideal is proper, or that is, an ideal is all of the ring if and only if it contains one. So an offshoot of this is an ideal is proper if and only if it doesn't contain one. So you can prove that an ideal is proper if you can show that one is not in there. Let's prove this. I think this is the easy way. I equals R. In this direction, we're assuming I equals R, and 1R is in R, which equals I. So there you go. That's not too shocking. The other way isn't difficult either, but it is a little bit more useful. Let's suppose that 1 is in I. Well, pick any element in R you want. So I picked a random element here, R and R. Notice that R when I multiply, since 1 is in the ideal and R is an element of R, I is a vacuum cleaner, so it sucks in. R times 1 over R is an I, so R is an I. Therefore, I is equal to R. I is always a subset of R, but we've shown that everything in R is also in I, so we have equality. This simple observation that an ideal is the whole ring if and only if the multiplicative identity is in that ideal will serve us later. Now, the next thing we want to talk about is, last time in class, I made the comparison between ideals and normal subgroups, right? In a group, a subgroup, you just have your garden variety subgroup and they're cool and all, but the normal subgroups are better because they're kernels of homomorphisms. Ideals are the analog there. The extra bit you get for normal, that is, in normal, the conjugate of the subgroup is still the subgroup. The ideals is this vacuum cleaner part. That's the analog here. Because ideals are the analog of normal subgroups, it allows us to build quotient structures the same way that we did with groups, right? If we have a normal subgroup N and G, then G mod N is a group under that multiplication that we have. We've got the same thing going on here in this situation with rings and ideals. So let me get right to it here. I'm going to use this proposition. I'm going to use this proposition to define some of my terminology kind of as I go here. Let R be a ring and I an ideal. And I in R an ideal. Now, I am going to build something similar to what I did back in the days when we were doing group theory in the following sense. I am going to do the following. So I am going to consider R mod I, these cosets. Now, so far, this is an old friend. And the reason it's an old friend is because remember, R is a group, towards a ring is a group, and I is a subgroup of it. And since R is abelian, it's normal. So these are just the old-fashioned cosets that we had in the days of group theory. The quotient group here can be made into a ring and here is the way that with multiplication defined, well, I'll call it. Again, I like this rule for multiplication because in a certain sense, it's as simple as you can hope it to be. The coset x plus I is coset y plus I is the coset xy plus I. Right? And so let me kind of give you kind of the big picture here. So here's the way it works. Just this is a reminder. We already know how the addition works because that came from what we knew about group theory. So the way the operations work here, just as a reminder, is the coset x plus I plus the coset y plus I is the coset x plus y plus I. That's the abelian group theory part of it. And multiplication is x plus I times y plus I is xy plus I. Okay, Now, I wanna prove this proposition. I wanna show that, in fact, what I do get is a, good old-fashioned ring. So, let's do the proof here. And I am going to shortcut where I already know stuff. So, we already know that R mod I is an abelian group under addition. That's work we've done before. R mod I is an abelian group under addition. We know that the addition is well defined. We know it's closed. We know it's associative, all that business. What about the multiplication? Well, that's the new thing. We got to show that this multiplication makes sense, and we've got to show that it plays nice with addition. Now, first and foremost, one of the first things that we did when we first defined the quotient group is we had to show that this addition is well defined. Remember, back in this addition here, if you pick different representatives, if your representative of this coset was x prime plus I and y prime plus I, we need to show that my addition, your addition, they give the same output. We've done that. We've done that for the addition. But now we have to do that with multiplication. How do I know that this new operation here is well defined? So that's going to be step one. We need to show multiplication as we've defined it here is well defined. That's the big thing that we've got on the front burner, because, I mean, why waste our time if this multiplication isn't well defined, if it doesn't even make sense? Well, so suppose to this end, and by the way, so far to show the well-definedness of addition, all I needed was the fact that I was a well, technically normal subgroup in this case. So the ideally part, the vacuum cleaner, I bet you is going to show up when we try to show that the multiplication is well defined. Okay, so what I'm saying is tomato, tomato. I say tomato, my coset is x plus I, but you say, hey, I've got another way to write it, a plus I. That's your, whichever the other one was. I've got y plus I, you've got b plus I, right? Okay, so what does that mean? So x minus a and y minus b are both elements of I. That's what it means for these two cosets to be the same. The difference in y and b has to be in I. The difference in x and a has to be in I. Right? So if you look at, right. So what we want to do is we need to show that the coset xy plus I is the same thing as the coset AB plus I. So let's do it this way. A minus x is in I, so AB minus XB is in I. Right? What did I do? I multiplied A minus X on the right by B, right? And it's a right ideal, right? Because I is, in fact, what we said is an ideal. So this actually uses the fact that I is a right ideal, because it sucks in stuff from the right. Okay. Now, what I'm going to do also is I am going to multiply, I guess, let's see, y minus b times, I guess what I'm going to want is multiply this by negative x. Y minus b is an element of I, and when I multiply by negative x, I'm going to get minus xy plus xb. And this is also in I, but this time I use the fact that I is a left ideal. Because now it sucks in negative x, which is hitting it on the left. So I've had to use so far that it's a right ideal and left ideal. So it's not good enough for me to say anything other than ideal because I need multiplication from the left and the right to work. Okay, so what do I got? I got this animal is in I, and this animal is in I. So I can add them up. AB minus XB plus minus XY plus XB is in I. And conveniently, the XB's cancel. And I get AB minus XY is in I. And this is exactly what it means for the coset AB plus I to equal XY plus I. So what I've shown is I pick X and Y for my representatives. I get this answer. You pick A and B for your representatives. You get that answer and they're equal. Okay, so the multiplication is well defined. Fantastic. Clearly, the multiplication is closed, right? So that, what do I mean by that? I mean that when you multiply two things in R mod I, you get a new thing in R mod I. Why is that? Because if X is in R and Y is in R, then XY is in R. And so this is another element of R mod I. So it's closed. I need to show technically that it's associative. I guess I can erase this now. And maybe I'll do this one a little bit more thoroughly than be less careful with the other ones, because it's not too bad. Because if you have X plus I times Y plus I, Z plus I, where the elements X, Y, and Z are all in R, then this is X plus I times YZ plus I, combining these two. And now this is X, YZ plus I, because that's my rule. Now, the original ring R has associative multiplication. So because of the associativity in the original ring, multiplication, I can do that, which allows me to dissect it like this. And this breaks apart further. So this is X plus I, Y plus I, times Z plus I. So the multiplication is associative. What else do I got to do? Well, multiplication's got to be associative and it's got to play nicely with addition. So one more try. Again, I'm only going to do half of this because I really need to do it for both sides, but I'll explain what I mean when I get there. If you have X plus I times Y plus I plus Z plus I, well, I can blob this together as a single element. I'm sorry, Y plus Z. And now I can blob this together like this. Like that. Now, again, these animals right here, they come out of the original ring. And so I've got the distributive property there. So this is XY plus XZ plus I. Because I can break this up like this. And by definition, this is XY plus I plus XZ plus I. And for that final step to break it up, this is x plus I times y plus I plus x plus I times c plus I. So in other words, I distributed x plus I times this, x plus I times this. That's exactly what I got. Really, I need to check this from the other side. I need to multiply this thing on the other side and check it, but the proof there is almost exactly the same. Okay. Let me make a couple of remarks. And then we're going to hit up the mighty isomorphism theorems. Once again, we're coming up on the isomorphism theorem. You'll be very happy to know that the isomorphism theorems are very analogous to what you've seen before. So it'll almost be like an old friend. Okay, let me make a couple of remarks about the quotient ring. Note, if R is commutative, then so is R mod I. Right? I mean, if you look, how do you multiply things here? X plus I times y plus I is x y plus I. If the order doesn't matter with the x y, you can turn it around here too. If R has identity 1R, then R mod I has identity. And the identity here, probably no surprise, is the coset that looks like this. It's just the identity element plus I. And you can check in the multiplication that it functions exactly as you want it to. You multiply by any R plus I, and that's what you get back. Okay. So let's start off the isomorphism theorems, and we will start with everybody's favorite, my favorite, because again, the other ones kind of follow up from them. The first isomorphism. Okay. So first isomorphism theorem, suppose this is 929. Let F from R to T be a homomorphism of rings. Then I'm going to restate something that we've already discussed. Then image F in R is an ideal not image F, I'm sorry. That is curl of F in R is an ideal. The image of F T is a subring, and there is an isomorphism of rings. Again, just a homomorphism that's one-to-one onto F bar from R mod the kernel of F to the image of F, given by F bar of the coset R kernel of R plus kernel of F is F of R. Okay, let's prove this. And again, there's not much to prove here, really. Because our previous work in this vein has already done a lot of the heavy lifting, which is good news. So let's kind of assess what's done and what needs to be done. We know F bar from R mod cur F to image of F, given by F bar R plus kernel of F equals F of R. We have already proved in the group theory part, this is a well-defined function. And if you remember back to those days, that was really the heavy lifting, showing that this function was well-defined, was the hardest part of it, and we're done, because we already did it. In fact, we already know that this is a homomorphism of groups. Homomorphism of groups. So we have already shown that this map right here is a well-defined homomorphism of groups. I did insert these statements here that the kernel of F is an ideal and the image of F is a subring. We already proved that at the beginning of this class. So that really the only thing left is, and in fact, I didn't even write it up here. It's not just a homomorphism, it's an isomorphism. Because again, appealing back to the group theory, not only is that a homomorphism, but it's one-to-one and onto. It's onto the image of F and it's one-to-one. All that's been proved. The only missing piece here to make this statement about a homomorphism is just, it needs to respect the multiplication. That's it. That's all that's left. So we need to show F bar of X plus kernel of F. Let me write that, spread that out a little bit. Oops, times. Is F bar X plus kernel of F times F bar Y plus kernel of F. That's all that's left. It's just to show that this respects the multiplication. And this is actually fairly easy, because if we look at F bar of X plus kernel of F times Y plus kernel of F, this is F bar of XY plus kernel of F, because that's how you multiply those things. Now apply the rule here. This is F of XY, because that's what this homomorphism does. It just does F to whatever the coset representative is. And F, our initial assumption is, this is a homomorphism of rings. So this is F of X, F of Y. And now backtracking here, F of X is F bar of X plus kernel of F. And F of Y is F bar Y plus kernel of F. And there you go. So the first isomorphism theorem already done. And it is kind of groovy that we didn't have to do nearly as much work as we did earlier when we were setting this up. But the fact we already knew this worked for groups got us, I mean, at least 80% of the way there. Let me make a remark after this. This is also kind of analogous with what we had before. Given mark here. So here we have let R be ring and I in R an ideal. I is an ideal. Now consider I sub I from R to R mod I given by this is called the projection map. Actually, many of you have done this if you've ever done modular arithmetic, right? When we looked at an integer and then you go to Z mod n, right? It's similar to this. You have pi I projects from R to R mod I, it's taking x to its coset, right? We've already seen this map actually already done at the group level. G goes to G mod n. Notice that the kernel of pi I. So what values of x go to the zero element of R mod I? Well, that means that x has to live in I, so the kernel of this is precisely I. It's easy to verify that this is a homomorphism. In fact, we already know it's a homomorphism of groups. You should check that it's a homomorphism actually of rings. That is, all you have to do is check that the multiplication is respected. And this is the analog of yet another thing that we saw in group theory before, and that is a subgroup is normal if and only if it is the kernel of a homomorphism. The same is true for ideals. That is if you will, a subring of an R is an ideal if and only if it is the kernel of a homomorphism. Okay. Let me give you kind of an application to this, which is kind of a fun application, I think. It is a classical problem in number theory and algebra, and this, lest you think there's nothing but naval contemplation there. This actually has lots of surprising, in fact, applications. Here is a question. Example. Consider equals 2. Now, this is an equation that you want to solve. And this is why you might like rings for the following, because actually this equation, this is called a Diophantine equation. They're very, actually, one of the most famous Diophantine equations is Fermat's famous equation that led to Fermat's last theorem. So if you don't know this, I will take kind of a quick little step into fun land with this. Okay, let's consider positive integer solutions to this equation. And there's a lot of them, right? Of course, you could let y equals 0, let x equals z, and garbage like that. So let's ignore that. Let's just consider positive integer. There's lots of solutions to this, right? You've seen them probably in a geometry class when you looked at right triangles and so forth, right? For example, one solution is x equals 3, y equals 4, and z equals 5, right? 5, 12, 13. There's a lot of solutions to this. In fact, you can parameterize it. However, what about this? solving this equation is a little more elusive. I mean, as long as you don't let silly things happen like y to be 0 or z to be 0, if you demand positive integer solutions to that, I bet you won't find any because there aren't any. In general, there are no non-trivial, well, let me just say, there are no solutions to x to the n plus y to the n equals c to the n with x, y, z, and n greater than or equal to 3. There's a whole bunch of them for 2, not any for not just 3, but 4, 5, anything higher, you can't find non-trivial integer solutions. This looks like a fun problem. And there was a certain amount of mystique attached to it because this is called Fermat's last theorem. It was, Fermat was studying these Diophantine equations, and he had claimed that he had a solution to this, but it was too big to fit in the margin. Mathematicians went after this. It wasn't actually solved until around 1995, and it was solved with some very heavy-duty machinery. Very, very big machines theoretically were used to solve this in general. Special cases had been known and been built up, but the entire theorem took forever. This is the playground of ring theory, solving these equations. Why is this a playground of ring theory? Because to solve this equation or to solve these equations, you got two operations going on. This is asking you something. I take an integer and I square it, take another integer and square it, and then add them up. So see, you're using multiplication here to get these, you're using addition, and then it's supposed to equal something that's also been squared, right? Here what you're doing is, okay, I've got some integer x and some other integer y. When I square this, multiply this one by -10 and add them up, I want to get 2. Can this happen? Right? Solutions, yes or no? Perhaps it's hard to tell. And what's really confounding about it is there seems to be no end to telling it, right? I mean, maybe you start guessing things like, well, let me just make it easy. Y equals 0. Well, that doesn't work because x squared equals 2, and that never happens for an integer. So maybe I take y equal 1. Well, you know, that seems kind of problematic because now if y equals 1, I have x squared equals 12, right? Y equals 2. Well, now I've got minus 40. 42 is not a square. This is getting really old, right? This is really obnoxious. And the problem is I can make this big and I can make this bigger, and maybe there's some point where they balance out. They're very close together, and they give me 2. How can I tell? Does this ever happen? Does it not? And the answer is it doesn't. But the problem is with telling this is there's too many things to check. There are infinitely many things that you could look at for the values of x and y. So what I'm going to do is I am going to consider a homomorphism. I'm going to call it phi. It goes from z into z mod 5. Right? And actually, you can think of this as c mod 5z. So it's a homomorphism very much like this one. Here, r is being played by z, and I is all multiples of 5. But basically what I'm doing is I'm reducing this equation mod 5. And perhaps we'll see in a moment why I care about mod 5. 5 is a good choice because I've already done this problem. Let's see what happens. Suppose we have a solution A, B are in the integers, and A squared minus 10B squared equals 2. Apply the homomorphism here. Right? These things all live in the integers, so does this. Apply the homomorphism, and what you should get is, this is phi of A squared minus 10 phi of B squared equals phi of 2. Right? Because this is a homomorphism, phi of A squared minus 10B squared is phi of A squared minus phi of 10B squared, and I can do this. And I am going to call this what we usually call it. I'm going to call this 2 bar in mod 5. What is 10 bar? Well, notice that 10 bar mod 5 is 0 bar. So I get the following equation in Z mod 5. Now, let us take a look at Z mod 5 and see what happens. In the ring Z mod 5, let me make a table here of every element and its square. When I square 0, I get 0. When I square 1, I get 1. When I square 2, I get 4. When I square 3, I get 9, which is mod 5 is 4. And when I get square 4, I get 16, which is 1. By the way, this makes sense because 1 and 4 are negatives of each other, so they should square the same thing. Same with 2 and 3. Notice that in this column, there is no 2 bar, which means this equation is insoluble. Which means the original one can't have a solution either. Because if the original one had a solution, it would have given rise to a solution here. So there are no solutions in the integers to this. Now, let me point out that you have to have a little bit of care here because some of these Diophantine equations can be very deceptive. Just kind of for giggles, you might check this out. If you mess around with this in any kind of primitive way, you'll see that the only solutions appear to be when y equals 0 and x is plus or minus 1. And it looks for a while like that may be it. But the smallest solution, this actually has infinitely many solutions. And the smallest one, as far as the size of the digits, is x equals 2,143,295. And y is 221,064. So sometimes these things can be a little deceptive. I'm going to leave you all with the second isomorphism theorem, and we will talk further about that in the third one on Monday. Theorem 9.2.11, second isomorphism theorem. And this is going to look very much like the one for groups. It's very similar. Let A be a subring of R and be an ideal of R. Subring B in R an ideal. So B is a little bit stronger than A in that regard. Then A plus B and this is a very suggestive sort of notation. this thing right here is a subring of R. And the intersection of A and B is an ideal of A. So this intersection is an ideal actually of A. And here's how I want to tie them together, and this will look familiar. A plus B mod B is isomorphic to A mod A intersect B. This will look very much like the second isomorphism theorem for groups, and we will discuss that next time.